Okay, so to kick off this session, let's start with just like introducing the chapter 7 material. So we're gonna start with the closed energy balance, where there's no mass transfer across the boundaries while the process is occurring. So this is like a batch process. And the common simplifications, well, first let's start with the equation. So delta U plus the change in kinetic energy plus the change in potential energy is equal to the heat plus the work. And so this is the work transferred to the system from surroundings. From the surroundings. And most simplifications that we can make are based on givens, such as we can assume that delta U is 0 if there's no temperature change, no chemical reaction, or no phase change. And then for kinetic energy, we can assume that kinetic energy is 0 if there's no acceleration in the system. Well, the change in kinetic energy. And then for the change in potential energy, we can assume that that would be 0 when the system is not rising or falling. For heat, so we can assume that Q is 0 if we are told that it's adiabatic or it's insulated. So if we're told either of those, then we can assume that Q is 0. And then work, we can assume that work is 0 if there are no moving parts. Now for an open system energy balance where mass is transferred across the system boundaries during the process, we, instead of delta U, so instead of internal energy, we are going to have delta H, so change in enthalpy, plus change in kinetic energy plus change in potential energy is equal to Q plus shaft work. And shaft work is the rate of work done by the process fluid on a moving part within the system. And these same simplifications apply here. So you can make all of these same assumptions of things equaling 0 based on these different givens that you could have within your problem. Now for the key difference between internal energy versus enthalpy. So internal energy, or U, you are going to use that when you have a closed system. And enthalpy, you are going to use that when you have an open system. And you can relate the two of these by H hat equal to U hat plus the total pressure of the system times its specific volume. And then the steam tables, this is just like where you can find the steam tables, which is all the specific internal energies and enthalpies and specific volumes based on temperature and pressure. So that's tables B5 through B7. And like I said, here you can get the specific internal energy, specific enthalpy, specific volume. Oh, and let me just say, so delta H, so like once you get these values from the steam tables, you could you would apply that by like delta H is equal to the mass flow rate times specific volume out minus specific volume in, and this is going to be in terms of kilojoules per kilogram, and this is also in terms of kilojoules per kilogram. And then this is meters cubed per kilogram. So whenever you apply these, so you have meters per second, kilojoules per kilogram, not meters per second, this is a mass. So kilogram, kilojoules per kilogram, kilogram cancels out, you're left with terms of energy here.